Swayam Prabha. Digital India. Educated India.
Good morning. Welcome you all to the next class in this particular course on analytical, spectral and microscopy applications of inorganic compounds and nanomaterials. In the past two classes we have been looking at various aspects of the absorption spectroscopy. So let us continue with that, particularly in terms of applications, understanding whatever the principle we studied in the past two classes. Okay, I have already talked to you about in the inorganic complexes, there are not only the ligand based transitions, you also have the metal based transitions, and these transitions are even being modified because the ligand bonded to the metal ion and metal ion bonded to the ligand. So therefore the original ligand bands would get modified. That is basically a signature for explaining that the complex is formed. We also have looked at, besides the DD transitions, we looked at aspects relevant to the charge transfer happening from the ligand to the metal and from the metal to the ligand. I am sure you are aware what kind of a situation will make what kind of a transition. If you are talking about the ligand to the metal, ligand should have a filled electrons which are in higher in energy, and there should be a low lying empty orbital on the metal, therefore the ligand to the metal can take place. Alternatively, if the metal to ligand charge transfer should take place, then the metal should have the electron pair which is relatively in a higher energy state, higher energy orbital, and there should be a low lying empty orbital on the ligand side, which is generally possible with the pi systems, and this is what we have seen in the previous class. So let us now look at the kind of signatures that one finds, the kind of variations that one finds as a result of the variation in the oxidation state, coordination number, coordination geometry, type of ligand, variety of these things. So let us look at some of these in comparison with that. So if you compare, then it is easy to understand. Now look at this particular slide on the left side. That there are two absorption spectra. One is on the top, which is the cobalt hexa-aquo spectrum, and the one in the bottom is cobalt tetrachloro spectrum. For both of these, the cobalt is in the cobalt 2 plus. Okay, so this is overall 2 plus missing, but it doesn't matter. But this is the water ligand, this is a chloride ligand. So what are the differences that you will find between these two complexes? One is the water ligand, other is the chloride ligand. The second difference is that there are 6 ligands in case of the aquo, and there are only 4 ligands. So these 6 ligands means they fit to the octahedral, the 4 ligands will fit to the tetrahedral. So now you have essentially two differences. One is in the geometry, that is tetrahedral versus octahedral, other is in the ligand, chloride versus water. So if you look at the spectrum, it's quite different. This spectrum has very broad features, and this has a very much more sharper features. And if you look at the y-axis and compare, the whole y-axis in the aqua complex is 0 to 1 at most, whereas here it is 0 to 60. So there is at least a 50-fold increase. So 50 to much more greater than that increase in the intensity as you go from an octahedral complex to a tetrahedral complex. The position of these bands are changing because the aqua ligand versus the chloride ligand, and the intensity is different because of the octahedral versus the tetrahedral. I have already explained earlier the intensities in the tetrahedral, which is less symmetric geometry as compared to the octahedral, will have a greater the intensities. We have already seen because of the DP mixing. So now you get the ligand variation and the geometry variation, etc. Let us look at ligand variation alone without making the geometry variation. So here is an example. Start from a copper hexaquo. This is of course 2 plus, which shows absorption band somewhere here around 8 to 10 nanometers. Now you replace one of the water by one ammonia, then next to 2 waters and 3 waters, so one at a time. So you replace one at a time the water by an ammonia ligand. Now you go to the water 5 and ammonia 1, and that gives a band here which is 770. Then you make water 4 and 2 ammonias, so that will go here 690. Then water 3 and ammonia 3, it goes to 640, and then water 2 and ammonia 4 is 600. So you have shifted from 800 to 600 nanometers just by doing one change. No change in the geometry, no change in the metal ion, no change in the oxidation state. It is a change only in the ligand type. 6 waters, 5 water 1 ammonia, 4 water 2 ammonia, 3 water 3 ammonia, 2 water and 4 ammonia, and that changes from 800 to 770 to 690 to 640 to 600. Very smooth transition. So this is happening is what? Because the ligand is changing. Why? We know very well from the coordination chemistry, the ligand perturbs this difference in energy, which is called crystal field stabilization energy difference, crystal field difference between the T2G level and the EG level that we have already known from the coordination chemistry point of view. Okay, we can also look at another example of very similar in nature but with a different metal ion. So here it is a copper 2 plus, which is a D8. Let us look at the chromium 3 plus, which is a D3 system. Here we have a chromium with this full line is chromium with a hexaquo, and you have another compound here, a spectrum is a chromium tris ethylene diamine, again 6 coordination, and then chromium hexacyano, again 6 coordination. So here again we have a chromium 3 plus, the same D3 system, all are hexacoordinated, therefore octahedral. Then what is the difference is the water replaced by ethylene diamine replaced by the cyanide ligand. So you can see the corresponding band, which is coming somewhere around 16,500 centimeter inverse, goes to 21,500 centimeter inverse in ethylene diamine complex, and then when it goes to the cyanide, it goes to 24.5. You see, the 16 to 24, its 50% raise is there. It's called 150%. That's what you call. So 16 plus 8, 24. So huge. And this also we know that the strength of the field of the ligand field changing from water to nitrogen, which is ethylene diamine, to the carbon, which we have already studied every time, always in the coordination chemistry, starting from 12th standard onwards. So that means whatever the coordination chemistry principles we know already, applying that one, you can explain the absorption spectra. So now we've explained this in the later stage when we go for the application of these into various establishing the structures, establishing reactions, products, it becomes very easier. So let us move on to a little further, and you know, in the D transition elements you have the D1, D2, D3, D4, all these kinds of configurations are there, and some examples are shown for aquo complexes of this. All these are MH2O6N plus. So in one case here is a D1, which is titanium 3 plus, a D2 which is vanadium 3 plus, and D3 which is chromium 3 plus, and the D4 which is the chromium 2 plus, and the D5 which is manganese 2 plus, and D6 which is iron 2 plus, D7 which is cobalt 2 plus, D8 which is nickel 2 plus, and D9 which is copper 2 plus. So what I wanted is, you don't need to remember anything, but just see there are differences, the shape of the bands, nature of the bands, and the area of under the bands, the number of bands, and then one very important thing is, if you look at the axis, y-axis, that tells you about the absorptivity or molar absorption coefficient. Here it is 0 to 5, 0 to 10, then 0 to something like 20, and 0 to 5, etc. But here you see 0 to 0.5 or much less, very, very low. Then here you have, so it is y-axis differences also you need to compare. The number of bands, shape of the bands, splitting of the bands, the sharpness and breadth of the bands, and the absorptivity, all of these. So that's how these change from D1 to D2 to D3. To explain the number of transitions, one needs to study the Tanabe-Sugano diagrams for the electronic transitions, which is not a part of this particular course, but will not go into this particular course at all. That one needs to supplement from other known sources. So you need to compare the range, the epsilon, number of bands, width of the bands, position of the bands, symmetry of the bands, etc. So from that you can differentiate one spectrum versus the other, and then that will be helpful. So for example, here if you talk about this kind of electronic configuration, I've already mentioned in the previous class that the spins are all in the same direction. If I take any one of the ground state spin to the EG level, they cannot pair because they are in the same direction. So therefore spin forbidden. So one needs to please have a look at this. So there is not. So in that case you need to change the spin, then only it will be possible, which means that you require to apply the higher energy kind of thing. So another example shown here, manganese water complex, which is shown here, shown in an expanded version, but why it is shown here is expanded to look at the y-axis and appreciate 0 to 0.15. So very low absorbance value, very highly low epsilon molar absorptivity value. This is because we have already seen earlier in the previous class, these transitions in the D5 with a high spin, they are both Laporte forbidden as well as the spin forbidden kind of things. Both of these things are there. So therefore they are very weak and then very sharp as well. So you may look at it as if it is a huge, the intensity you should look at the y-axis, you should not look at just the peak in isolation. And there are other peak assignments that they are not necessary for this particular course at all. Let us look at a case example further analyzing this. We look at the titanium 3+ hexaco, which was also shown on the previous slide. Now it's shown with a little expanded version. So if you look at this, generally if you are not familiar with this, you will say there is one band here. But if you are familiar with the absorption spectroscopy, you will see there is a shoulder here, or roughly somewhere here, and then there is one main band is there. Now you take the other side, this is one D1, D10 - 1 is D9, D9 is copper 2+. So the copper 2+, if you look at there is one band very clearly seen, another band as a couplet, a doublet you can call it as. So one position here, other position is there. Now how do one explain? If you look at these basically Tanabe-Sugano diagrams, where you can build these energy levels using the term symbols, it is a D term, 2D term. The 2D term in octahedral field will split into two of these energy levels, which is the T2G and EG. And in the octahedral, the T2G will lie in the lower energy and the EG will be in the higher energy. So the transition will occur from this T2G to EG. But because of the asymmetric nature of the electron filling, then this EG further splits, because EG is a doubly degenerate, further splits. That's why you find two. So one band around 500 nanometer, other band around 550 nanometer, and that's what you will see here. There is one at the 500 nanometer, there is one more at here around 550 nanometer. Okay, so for the D9 system, it will be exactly same as D1, but a reverse the splitting will be. That is because in the D1, in the d orbital there is one electron, and the D9, in the d orbital there is one hole. That means 10 - 1, one electron less to the 10. So therefore hole concept. So it's reverse. So it gets reversed. So the T will go up, the E will come down. That's only the thing. But still you will find the here the ground state will split, there the excited split. In the titanium case, the T2EG level splits into two, which is excited state. In case of the copper case, copper 2+ case, it is the ground state which is the EG which will split into two. but the result is 2 transitions instead of 1 transition, what is expected from the doublet D. So it's one here, other is here. Of course, this position will be different because it's metal and the electron density is different. So therefore, you have a different kind. So this is, you can easily make out when you have in a higher wavelength, this is coming from the copper, and when you have at the lower wavelength relatively compared to this coming from the titanium. But the structure could be the same, the 2 doublet kind of a peaks that is coming up in both the cases. So if one wants to obtain the parameters of the crystal field splitting energy values and other things, so one needs to couple this absorption spectrum or correlate this absorption spectrum with the information that is known in the literature, in the coordination chemistry books, on the Tanabe-Sugano diagrams. So you have to make that will explain you what is the transition, and use that transition values here and then derive the value for the delta, derive the value for the B, all those terms. So I hope that part is clear. Now, so when you say the absorption spectrum from transition metal ions, unlike the organic compounds where you will talk about the sigma to sigma star, n to pi star, pi to pi star, etc., here you talk about the bands, the number of bands, width of the bands, epsilon value of the bands, all of these things you will utilize for analyzing, identifying, comparing the kind of species formed in a reaction, the kind of a product formed in any kind of a chemical reaction in that. Let's continue, try to understand these absorption spectra by looking at various examples and try to see how, what kind of a changes would influence. For example, here there is a set of compounds. You see, please look at the slide here. This portion is the same here, is the same here. So this is what is called the aryl imidazolyl 110. So imidazolyl 110 phenanthrene. So these are imidazolyl 110 phenanthrene. This part is 110 phenanthrene, this part is imidazolyl. Now this is connected with some aryl. So there is a phenyl, then this dimethyl aminophenyl, and then this kind of a. So this portion, main portion of this is common to all. So if you study the absorption spectrum of this and this and this, you will be able to compare easily what kind of changes are coming. But now let us look at, if you take this particular compound and add of course the spectrum here with one of that and the other band here, as you keep adding the copper 2 plus ion, so this band is increasing, this band is also increasing, there is another band increasing, something is going down. So therefore you have a crossing of this, and these are called the isobestic points. These are referred to as isobestic points. Okay. So that tells you that there is a complexation is occurring as I keep adding more and more amount of the copper 2 plus to the molecule. One is the ligand here, one is the structure. So what I am doing, adding a little bit of copper, little more, etc. At each stage you take the spectrum, and that is what is shown here. What will happen? These two, the nitrogens will start binding towards the copper 2 plus and form a complex. I will explain in a while more details on that on the next slide, but before that let us look at another aspect. So you can see the charge transfer transitions coming from these ones. Now if you take even the second one, this compound, which is with the dimethyl amino in the fusion, and here only the major spectra are shown. This is with the ligand, this particular one, and then you have the 2, which is this red one, and the 3. So the 2, you have very little small amount of copper is added, 0.3 equivalents of that with the compound 2, and then you find this spectrum. And in the third case you had a large excess, means 5 equivalents of copper 2 plus you add for one equivalent of this particular ligand, you start finding additional bands over here and then over here. So initially you have some interaction because this band is changing some extent and there is some absorbance variation here, but when you add excess amount 5 equivalents, you have a strong band here, you have another strong band here. Is it only with this? No. If you take the compound number 3, this one, and you do the same kind of experiment, you will find the similar kind of results. But of course the positions will differ because the ligand which is in the para position here is different from the para position here. Somewhat, not a lot difference, there is some difference. It is a dimethylamino. This is more or less like that if you forget about this part of it. So you have, and this is also not an innocent part, this can also get involved in the interactions as well. So that means when you add initially small quantity of copper 2 plus, you have some straight binding or complexation, but as you keep increasing that, other additional things are happening. So what has happened was, so for that some computational calculations were done here, and if you look at this copper, when it forms a complex with this ligand, this is done for the complexation calculations for this one. So you add the copper 2 plus with this, and 2 ligands of this with 1 copper 2 plus gives an absorption spectrum. So that means this absorption spectrum coming between 700 and 800 is primarily coming from this just copper 2 plus. But in other cases, there is a band between 400 to 500, 400 to 500. So this 400 to 500 is coming from, not from copper 2 plus, it is coming from the first one is copper 2 plus with the ligand twice. The second one is copper 1 plus with the ligand. Okay, so that is the kind of a thing that you have. So this is also the ligand twice. So this is copper 2 plus, which is coming in the range 700 to 850 nanometer, and this is the one which is coming around 400 to 500 nanometer. So this is from the computational values, and if you compare these values, this will go over here and this part is over here. So that means something is happening in the reaction. When you add, there is an electron transfer. From where it will happen? It has to happen from this particular moiety, and that becomes stronger and stronger as you make more and more electron releasing group. So you have just phenyl and then dimethyl and then this one. So you are basically releasing the electron from this pi system to the copper center. Then this, what you have added is copper 2 plus, and this takes up an electron from the ligand or through the ligand and then converts into this. Now I will explain you the title. The title of this paper is that intramolecular electron transfer. So intramolecularly the transfer is happening in copper 2 complexes. So you have a ligand, you have a copper 2 plus, then forms a complex with these kind of a ligands. So you have the ligand, then you add the copper, then you make a complex. After a complex is made, there is an electron transfer going from the ligand to the metal, and the metal to Cu2 plus becomes metal Cu plus 1, and the ligand some other oxidation products that I will explain you on the next slide. I hope that part is clear. Okay, these are all similar except for the electronic factors are changing. Just the phenyl, dimethyl aminophenyl, and then this one kind of thing. So that means you can apply the absorption spectral study even to study the intra-electron. Generally electron transfers are studied by electrochemistry methods, by measuring the redox, but when you study the electrochemical methods, you can also parallelly study the absorption spectra, because the absorption spectra are also changing in these things. So application of absorption spectra and intramolecular electron transfer leading to the reaction products. Intramolecular, that means you don't require an electrode to be supporting this. So as such it happens. How it happens? When the copper 2 plus comes and knocks the door of the phenanthrene. So this is the door of the phenanthrene, the 2 nitrogens, the copper coming there and then binding. That's what it is. So what is happening in all this, as I mentioned just a while ago, this is, you take example as R could be H, R could be dimethylamino, or could be this one. But other compounds we don't need to really worry. When you add initially, what happens is 3 of these ligands are coming, say one phenanthrene, another, other. So there will be, each phenanthrene is giving the bidentate, so totally 6 coordination. Temporally it forms, and that gives the absorption, the spectrum, here the increase, and then followed by you have the this one changing into the tetrahedral kind of. So from an octahedral, So initially you form an octahedral complex, then you form a tetrahedral complex. How do we know? Because tetrahedral complexes will show a greater the intensity as compared to octahedral complexes. We know that very well. So using that concept itself, we can understand this one. Now, as you keep waiting for some more and adding further and further, this copper complex now receives an electron from the ligand, because there is a push from this phenyl ring or further, and that is what is written here as an auto reduction. It's not like an automatic reduction, but it is an auto reduction is mentioned because there is no external means of adding the electron within the electron within the system itself. So that will, and if that electron comes from the ligand, what should happen? Ligand should get oxidized. So we should need to check. You can see that the oxidized ligands are also checked here. So this is one other ligand which is identified from mass spectrum. Is another ligand which is identified from the mass spectrum. You may not be very conveniently identify this from the absorption spectrum, but you can couple this with a mass spectrometry, and the mass spectrometry will tell you that this is additionally happening in this. So it has been proven. So when something is reduced, something should get oxidized. We know that, and we know that it is coming from the ligand, therefore ligand should get oxidized. You can see that ligand oxidation here. So this is a ligand oxidation here. You can see even the oxygen is getting attached to the sulfur moiety on this, because this is a very susceptible moiety. So you have the dimethyl amino, so hydroxyl is added here, and here the oxygen is added over here. So real oxidation is occurring, oxidized product further. Is initially the electron transfer followed by oxygen, and because it's in the medium, so therefore you have the oxygen being attached to that. So an oxidation is occurring at the ligand, and for a reduction that is happening at the metal center. Okay. So in this example, this not only explains just the absorption spectrum, just application, it will explain electron transfer process, it will explain intermolecular redox process, it will explain oxidative process of the ligand, reductive process of the metal ion, and it will also explain the initial complex formation, geometry variation. So many things are there. All of these are identified based on the absorption spectrum. I hope that example is clear by explaining these things. So what do? You take the ligand, slowly add your copper ions, and then look at the absorption spectrum at different concentrations of that. That's all is done, and then compared all the spectra of that. Okay. So this means that one can do a series of titrations of the spectrophotometric titrations, which are referred as. So the spectrophotometric titrations means what? You titrate the ligand with metal ion, or metal ion with the ligand, by following the changes in the absorption spectrum. Of that. So using that, you can get what kind of a complex is formed between the ligand and metal ion. That means whether it is a 4 coordinated, 6 coordinated, that kind of thing. So therefore that will help what is the complex formed, etc. And what is the rate of the reactions, that also you can follow with that, and you can find the association constants of these things by doing continuous spectra. Or if there is any protonation, deprotonation necessary in the ligand, then we can get the pKa values. So we can get variety of these things from the spectrophotometric titrations by making some little variation in their parameters that you are measuring. One example is shown over here. Let us take this one on the right side first, and then we will go to the left side one later on. This is this molecule. You can call it as a ligand. Kindly look at the slide, please. This is a molecule. It has some hydroxyl, phenol, nitrogen, etc. So this can form a nice chelate, and then this nitrogen versus this nitrogen, that can also form a chelate kind of thing, right? Now to this, if I start adding copper 2+ ions, little more, etc., and then I measure at each concentration, I measure the absorption spectrum. You see that, and they are going from 0 copper concentration to 8 millimolar copper concentration for a given 1 millimolar ligand or so. See, the absorbance is increasing quite a good way, and suddenly there is a saturation. Now if I pick up the absorption intensity or absorbance at each of the peak position and plot, that is shown in the spectrum in the graph B, is that on the x-axis I put how much of the copper 2 plus is added with respect to the ligand. So that is the mole ratio. So that is what is drawn here is the copper 2 plus by L mole ratio, and this is the absorbance. Okay, so you have increase, and so from this you can find out where the thing is. You can see that. So the increase here is very little, that means saturation. There is a dramatic increase here, it's linear, and this is the. So what is this showing? So at 1. So that means this is forming a 1:1 complex between copper 2 plus versus the ligand, and that is what is shown over here. And you can see this phenolic oxygen, this nitrogen, and this nitrogen, and in fact even this nitrogen also binds that nitrogen. So there is a 4 coordination, and then some the counter anion water etc. can fulfill the coordination kind of thing. So you can get the whole coordination complex that is formed just by doing the spectrophotometric kind of a titration in this. Of course we can have different kinds of examples of such things to make ourselves that we understand easily of this. I think I will continue that part in the next class. Thank you very much.